Let's design a frequency selective surface. First thing I'm going to do is going to project, insert HFSS design. And we're going to design just at the unit cell, right? And then we assume this is a periodic and planar. And then we're going to get the electromagnetic response for an infinite array. So I'm going to design a circular FSS. So I'm going to go here, draw a circle. It's the same thing as going here, draw a circle. I'm going to click here in the middle, and I'm just going to drag the mouse somewhere. And this is going to be my circle. If I click here and create circle, you have the center and the radius. Whatever value you have here in the radius, I'm going to create a variable called radius, and I'm going to put this as 2 centimeters. You can zoom out, scroll with the mouse or Control D, and I'm going to make a hole. So I'm just going to click on circle 1, Control C, copy, Control V, and create exact same circle. But I'm going to create radius minus width or circle W, whatever variable you want to create. And this is going to be 0.1 centimeters. So now you see that this is smaller than this one. All the variables, they stay here. If you click on HFSS design, you're going to see radius and circle. If you change this, you see that it's going to change the radius of the circle. But what I'm going to do is subtract. So I'm going to click on circle 1. With the control on the keyboard, I'm going to click on circle 2. And then I'm going here on subtract. And I'm going to hit OK. So here we go. We have our circle. And again, if you change any of these variables, it will change the geometry, right? I'm just going to keep as 2 centimeter. That's the radius, and the width 0.1. Okay, and this I'm going to assign as a metal. So I'm going to right click, assign boundary, perfect E. That's a perfect electric conductor. It's not going to make any difference for our simulation. You can, of course, expand here and change the color to whatever you want. And now I'm going to design the dielectric. So I'm just going to create a box somewhere in here, anywhere. With the Alt pressed on the keyboard, you can rotate. If you click on the left mouse button and Alt on the keyboard, I'm just going to create an arbitrary box. Because with this box, well, first I'm going to assign a material. I'm going to right click this, assign material, and you can change to any material you want. I'm going to use polyethylene just as an example. Okay, and here on create box, you can create variables as well, and that's what I'm going to do. I'm going to select minus W divided by 2. So W is going to be the width. Oh yeah, and the other point is going to be minus W divided by 2, and this is going to be 0. Okay, so the W, what I'm going to do is attach to the variable radius. So if I change the radius, it's going to change the width of this dielectric as well, right? And here X size is going to be W, Y size W. Here we go. And the width, I'm going to just use minus 0.5 centimeters. Okay. So here we have our unit cell. Now we're going to need to create an airbox and assign some special boundary conditions. So to create the airbox, what I'm going to do is select box 1, Control C, Control V. Going to be exactly the same, but I'm going to change this material, assign material to vacuum. Okay, vacuum. Okay. You can change the name of those solid bodies if it makes more sense to you. Like you can put this as airbox, and this is dielectric or substrate, whatever. So on this vacuum, if I click here and create box, I can also change the height. That's what we're going to need to do. We're going to create like a very tall airbox, I would say. So I'm going to put minus h divided by 2. H is going to be the height of my airbox. And I'm going to make 4 times the width. And this is going to be h. Okay, so here we go. If you want to see this, go see through the airbox, you can click here or here. You can change the transparency and the color. I'm going to click here, display wireframe, so you can actually see through the airbox. It might be a good idea to save this right now. Go to File, Save As, and save somewhere, FSS. Okay, now what you're gonna have to do is assign an excitation on the top and the bottom. So you want to compute the transmission and the reflection, right? So you right click and go to selection mode, faces, and you select the face on the top. You right click, assign excitation, and there is a port named flow kit port, and that's the port that we're going to be using. And you have to assign vectors, because if this is going to be a periodic structure, it's going to be duplicated in many different directions that you specify with these vectors A and B. Okay. Here you can assign the number of modes of this port. For simplicity, I'm gonna use one mode, but sometimes if you have high order modes, you might want to add more. You have a modes calculator that can help you with this task. I'm gonna click next and finish, and I'm gonna do the same thing with the port here, or the face here down on the bottom. Select the face, right click, assign excitation, port, flow kit port, and it already uses the same vector definition for the flow kit port on the top. Same number of modes, finish. Okay, now you have to specify a boundary condition on the sides of this airbox. So you go to selection mode, and now you select objects. So you're going to select the object again. Is going to be this airbox, and you right click, assign boundary, and there's this option couple, auto identify lattice pair. If you click here, it's going to say, hey, this is going to be periodic on this plane, X, Y, exactly where we want to be, and hit OK. If you expand here, you're going to see the ports, the flow kit ports, and now you have this lattice pair, right? So we're going to be duplicating this many times, like in the infinite times, actually. Okay, and that's all you need to do. You right click on analysis, add solution setup. I'm going to select auto. You can change balance, higher accuracy, speed. I'm going to simulate from 1 gigahertz to 3 gigahertz. Linear step as 10 megahertz should be okay. And hit OK. And if you go to simulation, validate, it should be all good. Just select analyze all. Okay, after a few seconds, we're going to see the results. Right click on results, create terminal solution data report, rectangular plot, and then you can plot the reflection and the transmission. I'm going to select flow kit port 1, 2, and here you see that at this frequency we're going to reflect. If I add S11, you see this. If you right click on marker, add X marker, you can actually drag down here. You see that at 2.35 there is going to be reflection. You can actually plot the fields in here and see how this is going to behave, which should be pretty interesting.